All right, let's dive right in. Today, we're tackling three of the biggest ideas in all of physics: work, energy, and power. Now, we use these words all the time, but in physics, they have these super specific meanings that, honestly, are kind of fascinating. They explain everything from lifting a book to launching a rocket into space. So let's get into it.
So to get our brains warmed up, here's a little thought experiment for you. Imagine you need to get a book up onto a shelf that's 1 meter high. You've got two choices. You can lift it straight up, or you can push it up a nice long 3-meter ramp. Intuitively, which one feels like it would take more work? Just lock in your answer, because by the end of this, you're going to know for sure.
First things first, what even is work in a physics sense? Because it's not about your 9-to-5 job. In physics, work is only done when you apply a force and it actually makes something move. I mean, you could be pushing on a brick wall with all your might, sweating, grunting, but if that wall doesn't move an inch, you've done absolutely zero work, no matter how tired you feel. You need both a force and some movement in the same direction. That's the key.
Okay, so when you do work on an object, you're fundamentally changing something about its motion. You might be speeding it up or maybe slowing it down. And it turns out there's this really beautiful, elegant principle that connects the work you do directly to that change in motion.
And here it is. It's called the work-energy theorem. This thing is like the master key to this whole topic. It simply says that the total work you do on something is exactly equal to the change in its kinetic energy. And kinetic energy, that's just the energy of motion. So if you do positive work, you increase its kinetic energy. It speeds up. If you do negative work, you decrease it. It slows down. It's simple, it's powerful, and it's going to be our guide through all of this.
Now, to really get a grip on work, you got to understand the forces doing the work. And as it turns out, we can pretty much sort every force in the universe into two distinct families. I like to call them the energy savers and the energy thieves.
On one side, you've got your conservative forces. For these guys, the path you take doesn't matter one bit. They're all about storing energy and giving it back later. Then, on the other side, you have the non-conservative forces. For them, the path is everything, and they have a nasty habit of draining energy away from a system. Let's go meet the first family.
So these are the neat, tidy, and predictable forces. We call them conservative because they literally conserve mechanical energy. They don't destroy it. They just shuffle it back and forth between kinetic energy, the energy of motion, and potential energy, which is stored energy.
So who's in this family? Well, you've got the big ones. Gravity, for sure. The elastic force you feel in a spring or a rubber band, and the electrostatic force between electric charges. The one thing they all have in common is that the work they do only cares about where you start and where you finish, not the journey you took to get there.
And that brings us to their golden rule. If you move an object on any kind of round trip and bring it right back to where it started, a closed path, the total work done by a conservative force is always zero, period. Think about lifting a book up. Gravity does negative work. Then you lower it back down. Gravity does the exact same amount of positive work. The net result? Zero. Nothing was lost. And hey, this takes us right back to our first question. Since gravity is a conservative force, the work done against it only depends on the change in height. So whether you lift the book straight up 1 meter or push it up a 3-meter ramp to the same 1-meter height, the work done against gravity is exactly the same.
All right, time to visit the other side of the tracks and meet the messier family, the energy thieves. These forces are basically responsible for energy being lost in almost every single real-world process you can think of.
And the usual suspects here are friction, air resistance, any kind of drag. And unlike their tidy cousins, the work these guys do is all about the path you take. The longer the journey, the more work they do, and the more energy they steal.
So their rule is pretty much the opposite. The work they do on a round trip is never zero. It's always a negative number. If you slide a box across a rough floor and then slide it back, friction is fighting you the entire way, both directions. It's constantly stealing energy from the box and turning it into heat. It's like this unavoidable energy tax you have to pay on any motion.
Okay, so we've got these two very different families of forces, both doing work. But how do we actually calculate that work, especially when the forces aren't just a simple, constant push?
I mean, think about it. When you stretch a spring, the force isn't constant, right? The more you pull, the harder it pulls back. Our simple formula, force times distance, just kind of falls apart in cases like that. So what do?
Well, the answer, and it's a really clever one, is to turn to a graph. This makes it so clear.
If you just plot the force on the vertical axis and how far the object has moved on the horizontal axis, the work done is simply the area under that curve. This is such a powerful technique because it works for any force. It doesn't matter if it's constant or changing all over the place.
Now, knowing how much work is done is one thing, but how fast you do it, that's a completely different idea. And that brings us to power. See, energy is the capacity to do work. It's like the total amount of gas in your tank. But power is how fast you're burning that gas. It's the rate of energy transfer, measured in watts.
This quote just hits the nail on the head. A kilogram of coal actually has way more stored energy than a kilogram of TNT. But the TNT releases all of its energy in a fraction of a second. That incredible rate of energy release is what gives it all its, well, power. We've built a really solid foundation here. But all these rules and definitions, they work great for simple cases. What happens when things get weird? When the very rules of the game seem to change mid-flight? Well, it turns out there's an even deeper, more fundamental way to see all of this.
For instance, think about a rocket. As it's blasting off, it's constantly burning fuel and shooting gas out the back, right? So its mass is changing every single second. Our classic work energy theorem, which kind of assumes mass stays the same, suddenly gets really complicated. So is there a more universal law that can handle even this? Yes, there is. We just have to shift our perspective a little bit. Instead of looking at force and distance, what if we plot an object's velocity versus its momentum? Now, momentum is just its mass times its velocity. You can think of it as its quantity of motion. If you do that, the area under that graph is always equal to the change in kinetic energy. This is huge because this relationship holds true whether the mass is constant or not. And this one graph shows just how powerful this idea is. For a normal object with constant mass, like a bowling ball, the graph is a simple straight line. Easy enough. For our rocket that's losing mass as it flies, the graph curves up. And, this is wild, for a particle approaching the speed of light, where Einstein's relativity tells us its effective mass actually increases, the graph curves down. It's amazing. One single graphical method can unify everything from a rolling ball to rocket science and even relativity.
And that brings us to one last, kind of mind-bending thought to leave you with. We've established that work depends on distance, but distance depends on your point of view, doesn't it? On your frame of reference. If you're on a train and you see a box slide to a stop on the floor, you measure one distance, but someone standing on the ground outside sees the train, the floor, and the box all moving, so they measure a completely different distance. So, who's right? Do you both agree on how much work friction did? That's a question that really opens the door to the nature of energy and relativity itself. Something to chew on.